Okay, good morning. I didn't want to waste any time, so some of these topics we have gone over, but we'll go without any hindrance, right, from chapter 7 to chapter 8, finish, do the problems, and then see what turns out to be at the end, okay? So do not please stop me until the end. So you wait if you have questions, write it down until the end when you can ask me. Work, if you apply a force, and if there is a displacement in the direction of the force, then work is said to be done. So there are two components that are required to do work. One is you need a force acting at a point, and the second, the point where the force acts has to be displaced, as you can see. And work is defined as the dot product of force and displacement. When you say it's a dot product, work becomes a scalar. Although it's a dot product of two vectors, it becomes a scalar. And it's defined as FD cos theta, where theta is the angle between the force and the displacement. Which means if theta is 90 degrees, because cos 90 is 0, no work is done. This is the case that I was telling you last time. If you move an object on a horizontal floor, you do not do work against gravity, because gravity acts vertically down and the displacement is horizontal, right? So theta is 90, no work is done. The unit of work is joule, which is nothing but Newton meter. And as I said, work is a scalar. Now we're looking at how to find the work done if the force is not a constant, if the force is changing. And in this case, you have to recognize that the graph drawn between force and displacement will be kind of like this, with force on the y-axis and displacement on the x-axis. As you can see that the force is changing, right? It's not a constant, it's a variable. And let's assume that the displacement is right from A to B. And to find the work in this case, you find the area under the graph. We've gone all over all these topics. This is a kind of review. Okay, so if you find the area of the force displacement graph, you get the work. But in calculus, the area is the integral, isn't it? So it's integral f dot d or f dot dl to be perfect, or f dot dx. And for a spring, because f is equal to kx, for a spring, the more you stretch it, the bigger the force you have to apply. So that's what this shows. K is called the spring constant or the force constant. So when you substitute that into the equation and integrate from x is equal to 0 to a maximum, and substitute for f as kx. K is a constant, it's going to be taken out. And integral x dx is x squared by 2. And when you substitute the limits, of course I've taken the upper limit to be x in this case, you get 1/2 kx squared. Now, if you draw a graph of what happens in a spring, you definitely see that it's a straight line, because f is equal to kx. And therefore, all you have to do is find the area of the triangle. And the area of a triangle is 1/2 times, you see the 1/2, times the base. The base is going to be x, isn't it? And the height is force, which is kx. So it's 1/2 times x times kx, which is 1/2 kx squared. So either way, you get it as 1/2 kx squared. That is the work done in stretching a spring. The next is kinetic energy, and how you can connect it to the work energy principle. As you know, kinetic energy is the energy of anything that moves. It's the energy of motion. The word kinetic itself means movement or motion. So kinetic energy is due to motion. It's the energy of an object that moves. Consider that a car moves from one point to the other and the displacement is d. And the initial velocity is v naught. The final is vf. And I'm assuming that you're trying to increase the velocity of the car. Don't you have to do work? You have to step on the gas. That means you're providing energy. You're doing work to increase its velocity. And we're going to find the work done in increasing its velocity from v naught to vf. And if we can find the work done, that will be equal to its change in kinetic energy. That's the work energy principle. Work done is always equal to change in kinetic energy. That's the work energy principle. We're going to use that. So we have to find the work, and work is given by the formula. Force times displacement. And you know that in this case we are accelerating the car from v naught to vf. Work is force times displacement, yet force is mass times acceleration. And acceleration is vf squared minus v naught squared by 2 times the displacement. That is what we get from kinematics, okay? If we use the formula vf squared is equal to v naught squared plus 2ad and rearrange for a, that is what you get. I'm sure that's clear enough. So, therefore now work is force times displacement, and I've just substituted for force, as you can see, times displacement, and the d's get cancelled. I've not shown that, but you can understand that the d's do get cancelled out, isn't it? And you get it as 1/2, and take the m outside. Or look at it that way. What is this? Isn't this the change in kinetic energy? Because that's the final kinetic energy. Take away the initial kinetic energy. So I've proved that work done is equal to change in kinetic energy. That's what is called the work energy theorem. Work done is always equal to change in kinetic energy. That's the proof. That also shows us that kinetic energy is given by the formula 1/2 times mass times velocity squared. So you get both. Kinetic energy is 1/2 times mass times velocity squared. Do remember that because work is scalar, energy is also going to be scalar. And it's easy to work with this, as you're going to see. Conservation of energy, conservation of mechanical energy. But before that, there are two types of forces. This is something that we did not talk about, not too much. There are two types of forces, conservative and non-conservative forces. Now, what is a conservative force? Watch this. If I lift an object from a certain point to another point, am I doing work against gravity? Certainly, yes. Now, first time you saw how I lifted it straight up. Second time, I'm going to lift it from the same point to the same point, okay, but this way. Is the work the same as before? The answer is yes. Because the work is done against gravity. And gravity is a conservative force. What do you mean by conservative force? The work done does not depend on the path taken, but only depends on the initial and the final points. You got it? So a conservative force field is one where the work done depends on where you started from and where you finished, but does not depend on the path taken. You could have gone straight. You could have gone a little bit back and forth. Never mind. So that's what you mean by a conservative force. What's a non-conservative force? The exact opposite. Best example, friction. If I had to move this object on this table, and watch. Surely if I moved it straight, as opposed to me moving it this way, everybody knows that in the second case, I had to do, tell me, more work. So that's a path-dependent force. Friction is non-conservative because the work done depends on the path taken. You see the difference? So there are two types of forces, conservative and non-conservative forces. Now that's what I'm trying to write here. Work done depends only on the initial and the final points. In that case, and if it does not depend on the path taken, depending only on the initial and final positions, that is a conservative force. And I'm giving that exact example that I told you. You lift it straight up, or you take another path. The work done in both of these cases is mgh, isn't it? It's mgh. All that matters is the change in height. And that's a displacement, so you measure straight. So it does not depend on the path taken. Gravitational force, like I said, is a conservative force. And if you go back to the initial position, what do you think the work would be? If you go around a closed path, in a conservative force field, if you start from a point and go back to the same point, what's the total work done? Zero. Because if you start from here and come back there, the net work done is zero. Because when you go up, you're going against gravity. But when you come down, gravity is doing work. So you're getting back the energy that you spend in trying to lift it up. Does that make sense? Okay. So the net work done in moving around any closed path is zero, if it is a conservative force. And that's the example. You go from one point to the other. If it is a conservative force, then the net work is zero. Now let's take a look at a non-conservative force. I've already told you friction is a non-conservative force. And that's my best example. That's not the only one. Viscosity is non-conservative. Air resistance, of course, isn't it? All these are non-conservative. Here work depends on the path taken, as I'm showing you here. The work done in taking it from A through the path A is definitely less than the work done in taking it along path B, for sure, if friction is involved. Okay, potential energy. Remember that there are two types of potential energy, at least here. There are many other types, gravitational and elastic. There are two types of potential energy. Gravitational potential energy is given by mgh, where h is the change in height. Okay, that picture illustrates everything. So the initial position is y1, the final is y2, and the change is h. So h is y2 minus y1, so potential energy is mgh. But if it's elastic potential energy, and one second, the symbol for potential energy is U. So whenever you see the caps U, that is potential energy. Okay. So we are saying change in potential energy. Okay. Elastic potential energy, or the change in elastic potential energy, is 1/2 kx squared, because isn't that the work done in stretching a spring? Same thing, because work done becomes the change in potential energy, where of course k is force constant and x is x2 minus x1, means how much it extended or how much the spring was stretched through. Okay. Simple enough. Two types of potential energy. Gravitational, mgh, elastic, 1/2 kx squared. Now, let's bring a little calculus into this. We should be able to relate potential energy and force. Can you? Easy enough, because work is integral f dx, isn't it? And you know that writing a differential is the opposite of an integral. So we can write it both ways. Work is potential energy. Remember, work is potential energy. So ux is negative fx dx. Plus, whenever you integrate, there is a constant of integration. Why the negative? Because think about you lifting an object. Aren't you going against gravity? That's what the negative shows. So that's how energy is related to force. And most of the time we try to get rid of this constant of integration by setting boundary conditions. You know what boundary conditions are? So most of the time what we're going to do is this. We'll take the gravitational potential energy at the ground level to be 0. So we can say when x1 is 0, potential energy is 0. You see, that's one boundary condition, isn't it? Makes that easier. So that's what I'm trying to write down there. C represents the initial potential energy. That's what I'm trying to say. That means C represents U at x is equal to 0. That makes sense? Therefore, if we say U is equal to 0 at x is equal to 0, that makes it much easier. In which case we can write ux is equal to negative integral fx dx, because now you can just totally forget about c, because c becomes 0 automatically. So now the other way of writing this is fx as negative dux by dx. So that should make sense, because ux is written as an integral of force. So force is, and this is going to be important not only in semester 1 but also in semester 2, when you study about electric and magnetic fields. This is going to be really, really important. Force is the negative gradient of energy. You know the meaning of gradient, don't you? Slope, gradient. So force is the negative gradient of energy with displacement. That's how you take it. Now the conservation of mechanical energy, which is going to be used in many problems. Conservation of mechanical energy just means that total energy is conserved. So let's consider an object at a height. If it has a mass m and it's at a height h, its potential energy is mgh, isn't it? At that point. And let's imagine that it's dropped. As it comes down, we do know that its potential energy is changing into kinetic energy. And at any point, the sum total of both will be exactly the same as it was at any other point. You got it? So that's what you mean by conservation of mechanical energy. So I'm saying at the highest point, kinetic energy is 0 because it's still not moving. And if you drop it, and just before it hits the ground, because the height is almost 0, potential energy is 0, but surely the kinetic energy, which is given by half mv squared, should be numerically equal to mgh. Did you get it? So whenever an object is dropped, because we know that the kinetic energy here is exactly equal to the potential energy at the top. Why? Because the other term is 0, that's why. Because actually you have to take the sum of these two and set it equal to the sum of these two. Okay, so now in this particular case, the total energy, which is k plus u, is going to be a constant. That is the conservation of mechanical energy. That's it. The total energy is a constant. What a simple but so useful idea. Now that's where we get mgh is 1/2 mv squared and v is square root 2gh. Okay. Now this only applies if it's a conservative force, isn't it? But what if there is friction? Friction is called a dissipative force. Dissipation means wastage. So if there are dissipative forces included, then you got to take them also into consideration. Did you see this? Now when you apply the conservation of mechanical energy, you're going to say change in kinetic energy plus change in potential energy plus the work done against friction. That should be 0. We're going to use that. You will see that as we do problems. So there are two cases. Escape velocity. Did we talk about escape velocity? I think we did. That's the minimum velocity required to get an object off from the gravitational field of the Earth. And I told you that it's 11.2 kilometers per second. Did we get to that? Now that's a derivation where you have to, just wanted to give you a head up on that. Okay. So the velocity, the radius on the surface is r1. And somewhere else the radius is r2. Work done surely is integral r1 to r2 f dr. Let's take it one step at a time. Isn't that the case? How do you find work? Integral lower limit to upper limit of f dot dr. Are you getting it, or are you simply writing? Okay. What's F? What's the force? Gravity. Gravitational force. What's the formula for gravitational force? Isn't it G m1 m2 by r squared? Okay. In this case, one of the masses is the mass of the object. And what's the other mass? Mass of the earth. Okay. So that I'm going to substitute that. So it's integral r1 to r2 negative G times the mass of the object times the mass of the earth by r squared dr. Because we're talking about gravitational force. And whenever you integrate, you take the constants out. And here you have G, small m, and me, all constants, isn't it? Take them out, and you have integral dr by r squared. Integral dr by r squared is negative 1 by r. And then you see there are two negatives. Okay, so constants taken out. Integral 1 by r squared dr. r1 to r2. I'm writing that again. No change there. When you integrate that, you get cut out one step. Actually, you get negative 1 by r. And then I've substituted the upper limit, the lower limit. Two negatives make a positive. You got it, right? Okay. So that's the work done. That is the work done in taking an object from an initial distance r1 to a final distance r2 against gravity. And that is important. That's very important. Okay, in this particular case, we're going to take u as 0. Didn't I tell you it makes it easy? When do we take u as 0? When the object is at the surface of the earth. Okay, so we're going to take it as 0. I told you that we take potential energy as 0, which is the maximum at infinity. Forgive me for that. Did you hear me? I told you first that you take the potential energy as 0 at infinity. Infinity is escape from the gravitational field of the earth. So that is what is written there. When you do that, you're going to get a negative back again because this quantity is gone, right? And then you have negative 1 by r1. Hold on. I just want to see whether you understood that. What is 1 by infinity? 0. Okay, that's why that term is gone. What do you remain with? Minus 1 by? Now there's only one r, so I'm just calling it, I need not call it r1 now. Okay, that's what happened. So that's the potential energy. It continues. And I'm waiting. Here. So when we project it from the surface, stop. What is that? On the left-hand side, what you see now is the total mechanical energy. Because you've given it a velocity, you've given it kinetic energy, which is 1/2 mass times velocity squared, and it also has potential energy on the surface of the earth, isn't it? Okay, when it just escapes, what's the kinetic energy? 0. What's the potential energy? 0. So now you on the right-hand side, you could write something, but you know what I'm going to do to that. Okay, that's a general case which I've written, a general condition. That is just the conservation of mechanical energy. I just wrote the whole thing down. But now I'm applying the condition. If the object just escapes, then that becomes 0. Both become 0. So the entire right-hand side is 0. Therefore, now wait. Now I can call this the escape velocity. See that? Because it escaped. And you get the formula. That is the radius of the Earth. Just rearrange this, get the masses out of the way because they cancel out. Because when you take this to the other side, it's going to become positive, isn't it? And then cancel the small masses out, small m's I mean, and then you get the escape velocity as square root 2g mass of the Earth divided by the radius of the Earth. Square root of 2. And all these constants. So if you substitute the values of the mass of the Earth, the radius of the Earth, and the gravitational constant, you're going to get a number, which is going to be, I'm talking about the Earth, of course. You're going to get 11.2 kilometers per second. So you can check that out. When you get a chance, plug in all those numbers, and of course you're going to get it in meter per second. You will get it as 11,200 meter per second, which is 11.2 kilometer per second. So could we find the escape velocity from any other planet? Yes. All you have to do is you need to know the mass of the planet and the what? The radius of the planet, right? Mass of the planet and the radius of the planet. If it's a compact planet, what do you mean by a compact planet? Dense. Which means it has a big mass but in a small radius, then the escape velocity is going to be bigger, as you can see. The numerator is going to be big, the denominator is going to be... That's why when you come to black holes, if you have ever heard of black holes, they have so high a density that even light that the star produces cannot escape from itself. The black hole is actually a star that is producing light, but the escape velocity has become so high, if you're listening to me, because it's so dense, the escape velocity is so high that even light cannot escape from the star. So we call it a black hole. We'll come to that later on. But this is an interesting topic like any other in physics. And the last topic that we have is power. The last one. Power is the rate of doing work. How fast you do work. Power is work over time. The unit, technically joule per second, but it's also called? Okay, I think I mentioned the name of the scientist, James Watt, and his contribution, did I? Okay. And this is another formula that could be useful, because when you split work into force times displacement, assuming they are in the same direction, and then you know that displacement by time is what? Velocity? So you can also calculate power multiplying force with velocity. So that's another way of finding power.